are looking at how we might be able to use this instrument to screen post-mortem toxicology samples. And I say I struggled because a lot of the stuff that we tried didn't really work real well. So I suppose looking at it as the wise person, there's stuff to be learned out of stuff that doesn't work as much so as stuff that does work. So what I put together was stuff of what we tried, where we got to with stuff, but you know, this certainly isn't the end of the story with it. As I've said, I'm a real proponent of the equipment, less mass center, and it's a sensitivity issue, and I think those are things that can be overcome. Certainly the software issues can be overcome, and I think there are some things with sensitivity that may be coming down the pipe that could help that out as well, and could make this really quite potentially useful even for biological specimens. So even though a lot of what I've got here doesn't exactly paint the most optimistic picture for it, that's not what I want you to walk away with, so keep that in mind. Couple of things to say up front. We were funded on an NIJ grant, just finished this one end of July. And I was in the military, so it got ground into me that everything has to have the disclaimer on it that if it's correct, it's NIJ's fault. If it's wrong, it's my fault. The stuff that we were trying to do in our study was to evaluate the Joel Limited AccuTop DART as a novel application in the use for post-mortem toxicology laboratories, specifically looking at it qualitatively. We really never did anything quantitative with it. There's been some folks have done some quantitative stuff with it. FBI has done some quantitative with GHB. If you really haven't tried anything quantitative. I mean, there have been a few quantitative attempts with it. We were looking strictly qualitatively, looking at it as a screening methodology. So any of you that have dealt with post-mortem tox, it's not that dissimilar from drug chemistry screening. You've got a bazillion different compounds that might possibly be present, a limited number of tools to be able to try and figure out of the universe of things that might be present, what actually is there to move on to something more specific, like LCMS, MS, things like that, to do your quantitative and ultimate identification of the stuff there. So if you can expedite screening, you expedite a lot of stuff, because screening takes a lot of time, effort, energy, and doesn't necessarily pay off a whole lot for you. So specifically, we were looking at post-mortem samples, the icky, sticky, ooey gooeys, urine, which after a while turns into an icky, sticky, ooey gooey. Certainly blood and tissues, which can be very foul a while after. Primary, how many people were tox type stuff, dealt with any tox kinds of things? Okay, so a lot of toxicology analyses. Probably the primary two samples that you get, one are urine and two is hemolyzed blood, what they call gray top tube blood, which is hemolyzed with potassium oxalate and sodium fluoride. So it's akin to pancake syrup, and I'll try not to put everybody completely off their breakfast, but it's a problematic sample. You get a lot of the same kind of gray top tubes go in for alcohol analyses. It's reasonably good preservatives, but everything in the blood is hemolyzed, so it's just this kind of homogeneous goo, except for when they don't shake the tube up right, and then you end up with a big clot in there and other problems. So they're not particularly standard samples. There's a lot of variety between samples, even a lot of variety within the same individual that samples have been taken from. And what I'm going to try and do here with talking today, give you a bit of an idea of what we've set up at RTI. Talk a little bit about what we've done in terms of running standards. We really had kind of a three-stage approach to this. One, we took a big box O drugs and ran them on the DART to see, can we get these things to fly and show up like we'd expect? If yes, great. If no, I don't know what happened to it. Then we moved to putting those into urine. Since urine's a lot cleaner, a lot neater, concentrations are higher, it's a simpler matrix. Saw what we could figure out there, and then moved into blood and tissue stuff. Figured out what we could do there. And along the way, we had the opportunity to play with some of these samples on a variety of mass spectral platforms. We played some with the isomer separation and some fragmentation, though not nearly to the same level that Bob's done. Well, I mean, in toxicology, you know, if I've got a sample that has something that looks like 304.154, first thing I'm thinking is not scopolamine, I'm thinking cocaine. And I don't have to try and prove in that sample that this was cocaine, because that's the evidence. I'm trying to look in that to see, is this something that I either need to go try now to confirm for scopolamine or cocaine? I'm going to take it on for a second test, LCMS, MS, GCMS, whatever, and that's where I'm going to look at it as if it's cocaine and quantitate whether it's cocaine or not. So there's less demand to try and separate out those isomers for what you're typically doing in toxicology. So we'll talk urine-based stuff and then talk about the blood and tissue stuff. Give you a bit of a summary of our experience with the instrument. Now, I think everybody's starting to get the idea that it's very new technology. It's really only been around 2-3 years. You think about that in comparison with everybody's experience with GCMS, LCMS, LCMS, MS. It's a lot longer history with it there. So our experience, hopefully, is something to learn from, but that's not necessarily the experience you may have with it, because even, you know, all instruments have their own personalities. These things really have their own personalities. They're all a little schizophrenic, too. Talk a little bit about some of the future work. We've already chatted some about like the database issues and some things like that. So I guess we lose Chip someplace. It's all right. I'll be less nervous without the inventor sitting there. Chip has been very good sport about my complaining about their software now for a good couple of years in every public venue I can find. So there he is. Good morning. So what we've got at RTI. And just in passing, RTI, we're in Raleigh, North Carolina. RTI is an independent, not-for-profit research institute that was founded by Duke, UNC, and Chapel Hill about 50 years ago. Our group within, RTI is an enormous organization. It's got about 2,800 people that work for it. It does everything from coal gasification to government building in Iraq. Our little group in forensic sciences has predominantly dealt with the National Laboratory Certification Program, which is the certification program over workplace urine drug testing laboratories that operate under federal certification. We do a lot of proficiency sample manufacture, oral fluid, hair, urine, serums, everything from AIDS drugs to drugs of abuse. We've got a number of research projects that we run, mostly funded on NIJ type stuff. So we do a gamish of stuff, but that's kind of the framework of what we are. So we've got a Jolt off. We've got a Dart. Handy that, given I'm here talking about these things. We have, and actually we don't now, but while we were working on this, we had an auto sampler from Leap Technologies, and I think I'll have to leave it to Chip to try and describe what the relationship is between Leap and Joel. I don't understand it. Leap.
In short, IonSense is a spin-off of Joel, and there we go.
Did I get it on? There it goes.
The company that makes the jar is called IonSense. They're a spin-off company from Joel USA because Joel USA doesn't manufacture anything. They're just a sales and service organization. And IonSense has licensed Leap to sell the Dart as a sales rep.
Okay. Yeah, Scott Harris, who was with Leap and now is in New Zealand, I think is the one who really kind of came up with the design concept of this particular auto sampler and how it works. It's based on a CombiPal, which some of you may have run across on some LC equipment as an auto sampler for that, or some headspace equipment. CombiPals are used on some of those. It was based around a CombiPal auto sampler. So we've had one of those on the instrument. We have the Mass Center software up until very recently. We just got, and I don't think I spelled Schrader right there, but I can never figure out how to spell Schrader. It's German, right? Very recently we've had the Schrader software, so I've had the chance to play with it for maybe a grand total of about an hour so far. So most everything we've done has been with the Mass Center software. So here's our happy little TOF Dart. So right there, obviously, is the Dart source. Y'all getting used to that picture. That is the LEAP auto sampler system. So it sits on top of there, and I've got a little video of it here so you can see how this thing runs. And then the other thing we were talking about was this gas extractor. All of my chemists call it the schnorkel. It runs around the, here's the opening of it. I mean, it really looks like something out of the Muppet movie. It's got a flexible tube that runs back to a little box back here that's got a fan in it and carbon filters, and it just sucks stuff around and filters it out on the carbon filter there. If you're interested getting up to it, I've got cards, contact information. Give me a holler. I can give you the information on the one we got here. Ours was like, I think, $300 or $400. It was really pretty inexpensive. FBI, they've got a floor model unit that probably pulls a lot harder than this one does, but there's just not that much flow down here. So you can position the thing over here. You could even get it positioned over so that it didn't interfere with the auto sampler. And it really does help keep down the odors and stuff. Like I say, all of our chemists were perfectly happy until I started bringing in rat poison samples, and then they objected. So then we got that. So our little video here of the way this runs, and I think it pops up larger. There we go. So it starts out, there's a 96 well plate in the back. It picks up a tip that are, I mean, they're just the glass rods in a little plastic holder that fits onto that end, dips it into the sample well in the back, brings it over to the orifice, moves it through there, and you can program all of the various steps, how long it takes, how far down it goes, and then it moves back over to the very precisely designed tip extractor and pulls off the tip into our specifically designed waste bucket here. So you can see real quick, and it can just crank through those, crank through those, crank through those, crank through those. Found some real advantages with it that much more precise and reproducible in putting that sample in there and moving it through the stream. I think Eshwar is what he figures there's maybe about a 2 millimeter by 2 millimeter sweet spot in that stream. So, you know, hitting that spot to get the best sensitivity time after time after time is tough. Eshwar and Roman up at FBI, they've got, I like their little gizmo. They've got a little stand with an alligator clip on it that they went down to the hardware store and got some pieces of, got a piece of aluminum screen, and so they cut a little square of screen, and then they'll take a pipette and put a little drop of whatever it is they're going to sample onto that screen, and then set the screen into the stream so that they can reproducibly put the material back in the same spot every time on this screen, and then as the gas flows around it through that screen, it ionizes, evaporates stuff, and moves it on through with just this little piece of screen in there. And that's actually, I think, a lot of their GHB quantitative stuff they've done using that, because the biggest challenge they had with the quantitation was reproducibly making the peak. Putting it in there by hand, the peak shapes are wiggy wonky, and you needed a much more precise peak shape for on the tick. Just because how it gets introduced, you know, over the time that you are introducing it in there, the peak shape changes and would really impact their ability to quantitate based on that shape. So they could get a much more precise peak shape doing it that way. Or with the autosampler, you can get much more reproducible peak shape as well. And what we were finding is at lower concentrations, which funny biological samples seem to have that a lot, you could get better peak shapes in the mass peak shape because you're just more reproducibly there. You basically improve sensitivity because you're more reproducibly in that sweet spot. So certainly if you've got any questions about this is now, it looks a little bit different what Joel is selling. I think it's a little stumpier version. The cross arm is a little larger and it has auto dart across the side of it, but it basically the same concept and same instrument. Well, I guess I was on there, we can run it again. So it's picking up from the 96 well plate, dip it down in there. And this was also where we found that the instrument has an exquisite sensitivity for ethyl acetate. So we tried to extract an ethyl acetate. So in our 96 well plate, we had dozens of samples out over there open in 100 microliters of ethyl acetate. And when we ran it, we didn't see anything but ethyl acetate because it was all coming up off 96 well plate and coming across the orifice, and that's all you could see was ethyl acetate. It obliterated everything else. So large quantities of ethyl acetate around the instrument can be real problematic. You can't, if it's low enough, you could do like what we've talked about of subtract it out of the background because it would be consistently there. But when it's that close and that much, it interferes with everything, and you really can't see anything else. Yes, question?
Are you doing any sample prep or? Okay.
Yeah, I'll get there. I got lots of slides about that. Yeah, sample prep. In large part, what we've been working on has ended up being about sample prep because ultimately, for biological samples, sensitivity is probably the single largest challenge for the instrument. So we've tried a wide variety of ways to try and address getting more concentration and more just simply signal there, less noise, more signal. The balance to that is one of the things we set out for with this was a real advantage of the instrument is my ability to take a sample and rapidly screen it. So everything I do in terms of sample preparation puts me one step closer to just go run it on the GCMS I've always used. Why do I need this instrument? So we've tried everything we've been doing. We've been trying to steer towards as minimal a sample preparation as we can to mixed and varied success. I think everybody's getting fairly used to the idea of how samples are introduced. That upper one is the auto sampler, a little closer up of the auto sampler, putting it into the stream, and down here, obviously the orifice there on orifice 1, and introducing a tablet. It's a Percocet tablet that now has lots of burnt spots on it because I think everybody sometimes the dog and pony show, whenever somebody shows up in the lab, is pull a 20 out of their pocket and stick our Percocet tablet in there. So again, where we started out with this of what were the advantages, and probably what a lot of you have heard about this, the minimal sample preparation, broad range of sensitivity. You've got a TOF stuck on this. Hypothetically, you should be able to see anything and everything on the planet that might be present in the sample, hypothetically. Rapid analysis, you can see even with the autosampler, very quick sample acquisition. Now, data reduction, that's another story, but sample acquisition is quite quick. A real benefit for tox is anymore, the case is rare that only has one drug in it. Most of them, polypharmacy abounds. So simultaneously being able to determine the possible presence of a wide variety of drugs is a huge advantage in terms of tox screening. And the concept with this TOF that it has sufficient mass accuracy for reasonable formula determination. It's obviously not as high a resolution as some TOFs. It's not as high a resolution as an Orbitrap or something like that, but it's got high enough resolution that you can do quite a bit of formula determination with the data you get out of this. So we looked at 112 different compounds. We went through and picked stuff that, from our experience with post-mortem samples, we'd seen basically everything in this list. I mean, let's face it, it's really a pretty short list of what usually shows up in post-mortem samples. Those were the easy ones to put on the list. Some of it was just convenience of what we were able to find easily and find standards for. Out of that 112, there were only 4 that didn't produce an M plus H or an M minus H ion that we would have expected. One was buprenorphine glucuronide, which we're pretty sure we saw buprenorphine and glucuronolactone, so it broke apart there and we saw the 2 parts, but we didn't see the buprenorphine glucuronide. Psilocybin, and I think everybody's fought with psilocybin. THC acid glucuronide, again, I don't think, in that case, I don't think we saw either the THC acid and the glucuronide separate, and we never saw anything with that one. The other one was the 9-carboxy-11-nor tetrahydrocannabinol that we weren't able to see. So those are the only 4 that we never saw anything. Now that's not to say that we saw great ions for everything else, but those are the 4 that we couldn't see out of this list of 112. It included drugs, metabolites, ran the span, and all of this came out of methanolic standard materials. Okay, so this would be the simplest, prettiest, cleanest, easiest, just simply seeing, do we get what we would expect? Do we get odd losses that we need to be looking out for, things like that. So we put all of those spectra into the library, and right now, since where we're sitting on the end of the grant, I was a little hesitant about just bringing the library along for everybody. We'll get that sorted out and certainly have that available. It would certainly be something that we would then populate into any further database stuff that we'd work on. Odds are Bob's got a better library than we got anyways. So. Just put those directly in. This slide, ignore the highlighting. I had a brain fart there. I'm not quite sure what I was trying to highlight. I was looking at it last night going, what was I trying to say there? But we had, within our group of 112, we had a number of isomer pairs. So these would have been the drugs that have the same empirical formula. We can't identify them by their mass, the same mass. I think I was after, with the highlighting, the ones that probably are the most relevant and most problematic for us, that you're most likely to see actually both of them in a tox specimen and could be the most problematic for you. I think that's what I was trying to do when I was highlighting. So we got some of these, like the LSD. We didn't even bother with LSD. There's no way in God's green earth you're going to see LSD in an actual sample with this. So we were looking at the 2-oxo-3-hydroxy. But same thing, the LSD and LAMPA, you just really couldn't get apart. But, you know, like cocaine, scopolamine, the highlighting couldn't be ones that we couldn't get apart, because we can get cocaine and scopolamine. We can see those separately. But in our hands, the opioids, hydrocodone, codeine, and morphine, hydromorphone, norcodeine, we'd start ramping it up. We'd just get mush. We'd just get a whole bunch of fragments and really nothing particularly definitive on the other end. So I don't know what your experience has been on those, or if you've been any more able to break those apart reliably or not. That's what we ended up with. We really couldn't tell those apart. And then we also looked at what we were calling near isomers, those things that are close enough together in their monoisotopic mass that they're going to be problematic to resolve from each other. So, you know, they're within about 20 millimass units of each other. And I think here I really was after highlighting the methamphetamine TEA is probably the most problematic of those, because TEA is in everything. So you could, if you can't distinguish those, you may be looking at a peak you're thinking's meth and it's actually TEA. So our urine method. Any questions so far? Not seeing too much nodding off here, so.
Those masses weren't quite right, but it's
yeah, there's a big surprise. Every time I show a mass with him in the room, that's not quite right there, Pete. I'm mathematically challenged. Spelling challenged, too. So with urine, we took drug material, spiked it into blank urine. Took a glass probe. This is a very detailed and specific method here. Dipped glass probe in sample, put glass probe in dart. Repeat if necessary. Had the dart temperature, we were running at 300 degrees C. Calibrated the mass using the peg, same as what we've been looking at for the last day. Everything we did, we were doing it at orifice 1 voltage at 20 volts. Just kind of lit there. We really weren't after breaking stuff apart. We're trying to find a place where we'd get reliable M plus H formation and not necessarily a lot of fragmentation. And we had also archived, previously confirmed post-mortem samples that we were using all across on this. So they really were ooey gooey icky stickies, because they'd been sitting in somebody's freezer for at least a year. They were lovely. So what are things we saw? So this is just urine components. If you take urine, put it in there, things you will see. You'll see urea. And I love going from 2003 to 2007 versions. My circle moved there. The creatinine's the one just to the left of that. It's the 114, not the 121, is creatinine. And urine has a lot of creatinine in it, so you typically see a lot of creatinine dimer. So that pattern, the creatinine dimer is pretty typical of urine. You'll see those peaks basically throughout everything I show you for urine. So, a few of the drugs. Here's cocaine at 100 micrograms per mil. Keep in mind, most all of the units I'm showing here are micrograms per mil. So, kind of a large concentration. I mean, this isn't outside of the realm of possibility. I've seen in workplace urine drug samples, so people that are up walking around interacting with the world and driving, and actually that one was carrying weapons too because he was in the Navy, at mg per mil concentrations, benzoylecgonine in urine, so it's possible, but that is high relative to what you probably see in postmortem. So right here is the cocaine, and you can see there's the creatinine and creatinine dimer in there as well. There's methamphetamine right here. So again, you've got the creatinine dimer in there. Again, 100 micrograms per mil. Triazolam, just so you kind of get an idea of what things are looking like. Triazolam's out over here. So some of the limits of detection. Now we called limited detection what we could see in the urine that gave us a reasonable peak and was still within about 8 millimass units of what the theoretical monoisotopic mass was. So the problem is the smaller you get, the crappier the peak looks, the more your mass is going to crawl off just because the peak's distorted because it's small. So LOD wasn't simply that there was a bump there. There had to be a bump there that was still something in the neighborhood of the theoretical monoisotopic mass we were after. And so you can see we got kind of a wide range of detection limits. And keep in mind, this is all micrograms per mil. So this sits probably just north of what's really relevant in postmortem tox, even in urines, and even in overdoses for most all of these drugs. We range everything from trazodone, which just isn't even in the ballpark, at 50 micrograms per mil, to PCP, which that's maybe in the hunt for an overdose. And then I mark oxazepam here specifically because as we were going through this LOD stuff, so this is out of urine, oxazepam put us onto an interesting problem that we've encountered with this, and it comes back to what Bob was talking about with mixtures. Everything we were doing is a mixture. It's in a biological specimen, so it's a mixture of all kinds of schnutz. And in particular, in urine, we lit on, I kind of give away the story here, but creatinine, because it's present in massive concentrations in urine. So here's oxazepam out of DI water. So this is just 10 micrograms of oxazepam put into DI water. And there's the peak right there, nice mass match, looked pretty good, no problem there. But when we started trying to do oxazepam in urine, we couldn't find it. I mean, you know, in DI water, I mean, we're half what we were talking about of an LOD in urine there. It looks great. I mean, why can't we see that in urine? Well, when we started putting it in DI water, only with creatinine is the only other thing in there. So you've got, here's the creatinine dimer, here's oxazepam right there, still 10 micrograms per mil, but now if you look at the abundance, we're still in the same area as far as the axis height, and the oxazepam is a whole lot smaller. Okay, so if you start adding more creatinine, like 100 micrograms per mil, which is certainly a perfectly normal creatinine in a urine, oxazepam's getting pretty dinky there. And if we move on to 200, which is certainly within the realm of normal for creatinine in a urine, it's gone. So we call up Chip. You notice in a pattern here, something doesn't work right, call up Chip. Chip, what's the peak? Chip, what's going on here? We got to talking about it, looking at it, and actually I need to get back with him with our whole list of drugs to calculate these ionization energies for everything else. Oxazepam and creatinine have a pretty similar ionization energy, proton affinity. So in the stream, you'd think you should have massive surplus of ionizing capabilities there in that stream. Well, maybe not so much, because there's a lot of creatinine there. And probably the creatinine is interfering with the ability to ionize the oxazepam. So no protonization, you're not going to see it. It's not going to fly. So the mixture issues are a real challenge. Does that make sense to everybody what we're talking there? Nodding heads, not just nodding off, okay. Okay, so here's an archive case sample. So this was an actual post-mortem icky, sticky, ooey gooey urine that had methadone. Now this tripped us on another issue that we ran across. Again, likely this is a mixture problem. The fact that we've got an unknown gamish of potentially thousands of different compounds in a urine. We haven't even made it to blood yet. So we've got methadone, EDDP. This was previously confirmed for the presence of methadone and EDDP. And we've got both methadone and EDDP present there. But now if you go looking at stuff, the methadone mass, 310.213, and starts. Schrader, you can control the number of significant figures you got there. Mass center, not so much. But that's a pretty good match to the methadone. The EDDP, however, this is in the same scan, same spectrum. We've got methadone within 3 millimass units. Nice fit. EDDP, not close. What the heck are you supposed to do with that? If I were using this as a screening tool, the problem is with this, I'd say, sure, there's methadone there. That other thing, eh. Once you write out your SOP, you give some kind of range that you would say this is what's acceptable. Odds are it's less than 17 millimass units, and odds are you would not say EDDP was present. Probably, I don't have a really good explanation for this, but probably it's an unresolved mass that sits on that EDDP mass and has shifted stuff off in such a fashion we just really can't tell. The peak shape looks fine. I haven't really, as Bob suggested, gone in and looked at the isotope ratios to see if the theoretical isotope ratio that we should be seeing is screwed up, so it's actually something larger, that it's moved both that mass and the isotopes over, which would be who knows what, or if it's just that one mass that's moved and the isotopes are still okay, then probably it is more just a mass sitting on top of that. But we got a mixture. There's more stuff in there, and it comes out in odd ways. And we've seen this more than just here. We've had some trouble with amitriptyline. We've stumbled across it in various places. But this one was just a nice clean example where it was in the same spectrum. One's dead on, one's not even close. Okay. Questions about urine? Questions at all? Okay. Blood and tissue. Because of safety reasons and the fact that we didn't want you all to have the Hep B and Hep C series before you came here, I didn't bring any blood samples. I brought urine samples for you to play with. We spiked up a bunch of urine samples, so if we can wrangle it, I think it'd be great if each one of you go into the fridge, grab a urine sample. Bob or Chip can drive because I don't run the instrument enough to not make a complete fool out of myself and waste the entire 2-hour block trying to find the on button. But have each of you run through one of the samples and see what can be seen in these urine samples. We've spiked them at concentrations that you should be able to see and at concentrations that there ain't no way you're going to see it, in a variety of different drugs, ones that we've had work really well for us and ones that haven't worked worth beans for us. So it should hopefully give a spectrum of what's happened, at least as far as what we've seen in urine. But blood and tissue and what we've done. We're after, like we say, a fairly minimal sample prep method. And also what I will say on urine is we have tried just a liquid-liquid extraction to try and improve concentration. It really didn't help. In large part because I think when you start extracting and concentrating, yeah, you're extracting and concentrating your drug of interest, but you're also bringing along probably something else and concentrating it and creating problems. It's fairly easy to get it separated away from the creatinine with solid phase extraction or something like that. You can leave the creatinine behind. There may well be other things that you're concentrating and creating problems, and I'll show you here with blood what I mean. So we took some acetonitrile, put it in with the blood, so it's a precipitation, mostly get away all the proteins and things like that, shake it up, vortex it, spin it down, pelletize the gunk. Then we would pour off a little bit of that supernatant so that we could run that directly, and we'd take the remainder of it, dry it down, and reconstitute it in smaller volumes, so concentrated. So we'd precipitate this off, so it would be in part a cleanup step and in part a concentration step, and try it both ways around there. Again, the philosophy that we took at it was how can we do as little as possible to the sample and try and get someplace. Cases that we had 28 blood cases, we had 11 liver cases, a couple of kidneys, and a few brains sitting in the freezer. Most people would tell me that's where my brain has been, but mine wasn't one of those. Since we don't have any actual blood specimens here, I figured I'd throw in a bunch of pictures so that you can at least see and visualize what it is we were doing with them. So here's our blood sample that we've added acetonitrile to. Step 1. After vortexing. Now again, any of you that have done the tox side of things, you can get pretty artistic about this precipitation, and I have had cause, like with THC in bloods, particularly in small sample sizes, that when you go to do this precipitation, you ice everything down, have the acetonitrile as close to 0 as you can get it, ice your sample down, add the acetonitrile drop-wise into the blood so that you get as fine a flocculant as you can in precipitating the blood sample, so you don't occlude stuff in the snap giant clot that you form when you just dump it in there. In this case, this stuff was probably because of the age of the samples, didn't really just clot up immediately on us when we dumped the acetonitrile in there. So when you spin it, you see you got the flocculant all up and down the tube there. So then we spun it down, picture of our centrifuge there, and you get the nice little pellet down at the bottom. So now that supernatant is what we go to decant off that supernatant, leave behind the pellet. And obviously, in a step like this, there's a few things that we're not doing with this that were you to be doing an actual extraction step, probably you would have adjusted the pH of that blood before you put in whatever phase you were trying to extract over into. We really weren't trying to extract in the more classic term of extraction, where we were trying to partition a drug by changing its pH and its ionization state and drive it into an organic phase to separate it away from the other stuff in the blood. We were trying to do as quick and dirty to remove the big chunks and not a more selective extraction. So yes, we probably could get some improvements in sensitivity by adjusting pHs, moving it over into a more specific organic phase like you would do in a more classic analysis. But if I'm going to go to all that work, why am I going to go to this instrument? Then we dry it down under nitrogen, our little turbo vap here. So there's the tube and the turbo vap. Like I said, I'm trying to give you a flavor for the blood samples. And then reconstitute in a smaller volume. So we have a chunk of it that we just poured off that we just used straight, and then we had a chunk that we dried down to concentrate it. The other thing I want to mention is we did try with blood samples and tissue samples solid phase extraction. Specifically, we use this little system. I've had extraordinary luck with these over the years in a variety of settings, both post-mortem, sports performance testing, and workplace urine drug testing. This is the system that's put out by Spiware and the Cerex columns. They're a polymer-based column rather than a silica-based column. And I bubble effusively about what Phil puts out there, but I've had really good luck with them. I've had really good luck with them with a variety of technicians everywhere from, I know I had one that worked for me in Jacksonville who couldn't read, and we could get her to produce quite nice results, all the way up to very, competent, long experienced med techs that know far more than I do. It's a positive pressure manifold system, so when you close that thing up, it's got a plate, it pushes the rack up against it, and then you use nitrogen or just compressed air to push your washes and your sample and your eluent through it and collect it into tubes, or you can collect it directly into vials. We actually, in the Navy system, we had the Zymark rapid trace systems. We had banks of those things and jettisoned them in favor of this thing. The biggest downside to it is those columns cost like gold. Even in large quantities, they're probably $1.50, $2 a column. So they work really well, but they are expensive. So we tried solid phase extraction that we've had really good luck with. Like I say, in a variety of instances, and we use that both on the DART and, as I'll talk about in a minute, on a number of other mass spectral platforms. So like with urine, you see in blood some typical stuff. You see some urea, you see some monosaccharides, you see cholestyramine, and you see, hey Chip, what's this peak? Oh, that's a plasticizer. I don't know what plasticizer that is, but Chip says it's a plasticizer. But you see also there's lots of other little peaks, lots of stuff. So as in with a lot of toxicology, in comparison to drug chemistries, as a toxicologist, I get a whole lot less bent about other peaks and masses and stuff there. I don't know what they are. It's this stuff. It's a biological sample. It's just there. So as I go through this, you'll see a lot of other peaks that I have no clue what they are. But really, for the toxicology side of things, it doesn't matter as much. I'm more interested in being able to identify something that I know what it is and that it might be there than I am trying to identify positively everything that I see there. A little difference in philosophy. So, by an example, here's methadone. Now this is spiked into blank blood. Yes, I give a lot of things from my lab. Hair, blood, sweat, oral fluid, you name it. Don't say I don't bleed for my work. So this is 100 micrograms per mil again. Methadone in a blank blood. There's methadone right there. So this is just blank blood barbecued in there. So at 100 micrograms per mil, you don't even need to extract it. You can just barbecue the blood in there. Stinks, but it works. So this is 100 micrograms per mil methadone in blood, extracted in that acetonitrile, just straight, no concentration. And there's the methadone right there. So if you look, you're seeing probably about a 2-fold increase in the intensity of that peak. Now, if we go take that, it's like All in the House that Jack built, 100 micrograms methadone in blank blood, extracted 1 to 3 in acetonitrile, and dried down and reconstituted, there's the methadone. Quite pretty. So we thought, yippee, great. About, maybe a 5-fold increase there. So then we went down to 1 microgram per mil, something that's actually more biologically relevant in an overdose case. Blank blood, extracted 1 to 3 acetonitrile, dried down, extracted 100 micrograms per mil acetonitrile, and it ain't so great. It doesn't seem to be just a straight line from we have 100 micrograms per mil and all kinds of abundance down to 1 and not so much there. But if we go look at some post-mortem samples. So here's a post-mortem sample that was previously confirmed at 2.8 micrograms per mil for methadone. Run it just extracted, barbecue it in there, yeah, don't see anything. But if we extract it 1 to 3 in acetonitrile, no concentration, it's there. It's at least there. But this is what I mean by the LOD peak. It's there, but it doesn't look so hot. And when they don't look so hot, they certainly modify the mass you're going to get off of that. And as you notice, I'm leaving the profile data in all this. None of this is centroided, so you can kind of see some of the peak information. So now if we extract it, dry it down, reconstitute it, there's our methadone. Now it's starting to look like something more like what I might actually say from a sample. Oh yeah, methadone's there. So this is the liver from that case. So with liver, we homogenized it, fairly typical, like a gram of liver to 4 grams of water. Take the Cuisinart to it, grind it up. It was previously reported, and this is where it always gets challenging with tissues. Everybody reports tissues differently. What does it actually mean? It was previously reported as 6 micrograms per mil, so the homogenized material, a mil of that, 6.6 micrograms per mil in that, would have equated back to, I forget what in terms of grams per mil or micrograms per mil per gram tissue. but when we ground it up and extracted it, we did the same proportions, so when we were looking at it, we would be looking at the same value. Does that make sense? Obviously unextracted, it wasn't there. If we extract that, again, we're starting to see a little bitty bump there. Not something I'd be real comfortable going on with, but it's starting to show up. Dry it down, reconstitute it, concentrate it, now we're starting to see something real. So in this tissue, a pretty healthy concentration, but starting to see it there. So you can see it out of blood, out of tissue, out of urine. I mean, you can see them there. It's not impossible to do this. This is why I say we're at a sensitivity that's not really biologically relevant yet, but it's almost there, almost there. So we thought, great, we had such great luck with methadone, let's go look at a cocaine case, because as Bob and I were joking, this also seems to be an instrument that's a great cocometer. It just seems to have a sweet spot for cocaine. So, and this is the blood out of a case. This is blank blood that we were spiking. So 1 microgram per mil cocaine in this. So we're already looking at a much lower concentration of the cocaine. There's the cocaine right there, actually looking pretty good. Just extracted. Fairly good mass match. So then if we take it, extract it, reconstitute it, dry it down, there's the cocaine starting to look larger. So we went down to 1/10 of a microgram per mil. So now we actually are really talking something probably biologically relevant in terms of concentrations of cocaine. Do everything to it, and there's cocaine. I mean, like I say, it's almost there, even in a mixture. But this is nice, clean, blank, new blood, not icky, sticky, ooey, gooey blood. So let's go look at icky, sticky, ooey, gooey blood. Here's an aortic blood, previously confirmed at 0.52 micrograms per mil, so it would be 5 times what we were spiking in. Extracted in the acetonitrile, and yippee, it shows up. The only problem is the benzoylecgonine, cocaethylene, norcocaine, propoxyphene, norpropoxyphene, and something else that was in this sample. It didn't. But the cocaine was there. So if we dry it down, reconstitute it, and concentrate it, it didn't help much. So this is where I'm starting to say, as you start doing steps to try and concentrate, clean up, move stuff around, and try and improve your target, other stuff may come along. You also notice the mass on that one, even after much consternation, pulling of hair, and many multiple calibrations, isn't exactly close. So the peak's not all that hot, it's not really all that close. Something else happened in our nasty sample as compared to our nice clean blood sample. So here's what I was talking, the other drugs that were in this case. So there's benzoylecgonine, maybe? There's norpropoxyphene, maybe? Propoxyphene, maybe? These were all ones that were previously confirmed in this case by more traditional methods. All right. So, this acetonitrile thing may not work for everything. What if we do solid phase extraction on this? That'll fix everything, right? Oops. We didn't have a heck of a lot of luck with solid phase extraction on these things. It really didn't end up concentrating stuff. I mean, we're just the straight acetonitrile, we can still see the cocaine. Now we can't even see the cocaine after solid phase extraction on this. So it's a more complex picture trying to go about this of improving your sensitivity by modifying the sample. So we thought, well, these things have been sitting around in the freezer for an awful long time. Maybe those drugs just still aren't there. So we went to more traditional analysis now on these cases with how I would have normally done this, solid phase extraction. This is just the single quad LCMS. BE, cocaine, cocaethylene, all very nicely there. So it wasn't the sample degrading, it's something else going on there. In fact, as we look at some other cases, so here's a case, we've got cocaine, the kind of concentrations that were being reported in this. This is another case that we took onto many multiple platforms. So those are the kind of concentrations we're talking of, a variety of drugs in it. The other case, methadone, I mean, this is a pretty typical case. There's nothing unusual about these cases. So we went, and Agilent was very kind to help us out with this one. We'd like to try this out on many multiple manufacturers' platforms as well, but we went and looked across a variety of mass spectral platforms. So this is all the same LC stack, all the same LC conditions, looking at single quad MS, ion trap MS, 3D ion trap, straight up time of flight, Agilent's time of flight, a QTOF, so tandem mass spec with a quad and a TOF, a triple quad, and the DART TOF, and where we kind of ended up, that these archive samples across the traditional platforms really didn't have any trouble seeing the stuff that was in there. And quantitatively, they lined up pretty good with what was originally there. This would be, again, my brain fart down here. The DART TOF could detect the methadone in this case. So that was the case we were talking about earlier. And here on the TOF, this was really a shot in the dark. One of the things that I liked about this was we set up the solid phase extraction method. University of Miami was doing some DUI samples as well in the same time frame. We had like 2 days, 3 days in Little Falls at Agilent's facility there to go run this stuff on there. So we got solid phase materials in. University of Miami got the solid phase materials in, managed to get methods working, extracted, and onto the instruments and running in the space of about 2 weeks. So that's one of the things that I like about that particular solid phase system is it's real easy to get up and going. It's not real finicky. And you can drop it into a lab and usually get it up and running pretty quick. You pay through the nose for it, but it runs pretty quick. So the other thing that we had, though, was here on this, with the TOF one, I got that one highlighted. A lot of it, there was a lot of guessing going on some of the LC parameters as far as what ultimately our sensitivities were going to be. So in this case, we had too large an injection fraction, and it just blew away the detector. It was thoroughly saturated, so that's why we've got this kind of wonky number here. Big square-topped looking peak. So it may well have been closer to what we would have expected had we had a little bit better guess at how much we should have been putting on there. So if we look through at a variety of the drugs that we had in post-mortem samples, so these were stuff that was previously confirmed in samples that we were looking at, the green checks are the ones that we were able to see. May not have been able to see them very well, but we were at least able to see them. So acetaminophen, alprazolam, caffeine, carbamazepam, carisoprodol, cocaine, dextromethorphan, diazepam, ecgonine methylester, gabapentin, methamphetamine, methadone, meprobamate, mirtazapine, nortriptyline, oxcarbazepine, propoxyphene, quetiapine. Say that 10 times fast. Other ones we really weren't able to see, even though they were previously confirmed in those samples. It's a mixed bag. It's a mixed bag. I'm almost there. Am I on time for my break? You holding up okay? Reasonable sensitivity for some drugs. Not everything, but some drugs. Some things it's more sensitive for than others. Like we say, it seems to have a real sweet spot for cocaine. Other things it doesn't see so well. So now is that protonation, ionization, volatilization of these drugs to just get them into the gas phase? Is it something to do with the sample? There's a big long list of things that could impact why it seems more sensitive for some drugs than for others. But bottom line is it's not a universal detector. Guess what? Nothing is. It's better for some things than for others. And that's just a reality, I think, of all instrumentation, is they're not universally sensitive at the same level for everything out there. Duh. Creatinine seems to be a real issue in urine. More for some drugs than for others. Probably the only way around this one is extract it away from the creatinine. So a more traditional extraction where you're leaving behind the creatinine in the aqueous phase, manipulate pH to move your drug over into an organic phase or onto a solid phase column and leave the creatinine behind. There may be some ways to hydrolyze the creatinine, but odds are anything you're doing to try to chemically destroy creatinine is probably going to destroy your target too. So there's maybe some other ways to skin the creatinine cat, but creatinine can be a real issue for you. But larger picture of it, it's a mixture problem. There's got to be some level of sample preparation to be able to see anything. You may get away with it on the odd sample that you can just directly introduce it. Urine, probably more so than blood and tissue, but probably there's some kind of sample prep you're going to have to do to be able to see it. Now, I think there's a good chance you may be able to do something that's very quick, very dirty, very easy, and far better than what you're having to do on a tissue sample to get it ready to go to an immunoassay, certainly what you're probably having to do to it to get it to go to a GCMS screen or a GCMPD or something like that. So it's probably easier than that. So probably there is benefit to be gained in going this route. The autosampler is a big boon. It makes your sample introduction much more easy. It certainly is a lot less wear and tear on the individual that's got to run it. Probably the biggest thing standing in between that autosampler and nirvana is, dare I say, Mass Center. The Schrader software, what Chip's telling me is versions of the Schrader software that are just out there on the horizon probably will be able to make an autosampler actually function more like an autosampler. That you could set up a list, park your samples on there, walk away, and come back to data. Right now, with Mass Center, it's a mechanized sampling assisting unit, not really an autosampler. Because with the software, at least as we've been able to figure it out, you've got to start up a sampling run and you introduce a bunch of samples into that data stream.
Did you ever try setting up a sample queue in Mass Center?
It has it, but how does it can't trigger the autosampler?
Feed it a start signal.
Yeah, but it doesn't know when the end of the data set is.
No, I mean, you set a runtime like you would if you're doing flow injection.
Can you guys do that little?
Give him the microphone.
It's on me.
I'm just saying, Mass Center does have.
Yeah, it does.
I mean, I prefer recommend the Schrader software.
Yeah,
for this job.
it does. I mean, you're right. It does have some components in there. The autosampler right now has its own separate software that runs as a shell that you can set up a sample list in that software and it knows where to go in there. And what Chip's saying, he's right, that you basically can get one contact closure when you start a run out of Mass Center. And then there's no cue to the end of it other than you just told it how long the run might be. So, I mean, you could tell a fairly short run time that would be time enough for the autosampler to go around, pick up what you want in that data set, and then it would close itself down, start another. It gives you the one voltage change that would start the autosampler up again. You could make it work that way. And this is what I say is our experience has been with Mass Center straight up, and that's where most of my beef is. And what Chip is pointing out, and is very correct, that they understand what this is. They've got some issues within Joel that make it very difficult for them to deal with Mass Center. But on the Schrader line of things, there's a lot more potential. It's software. All of this stuff is solvable. It's not like there's some physical principle that's barring the ability to do this. It's software. So smart software people abound. They can fix this. It's fully fixable. It's just helping IonSense understand what is needed from the laboratories in terms of the software to make this something that works with what you're all up against in terms of trying to jam as many samples as you possibly can through too few people.
Just saying, what kind of report do you
Right.
want?
Right.
And then somebody has to pay for it.
Right.
It gets done.
But, I mean, that kind of thing out on the horizon is an enormous step forward for this really being something that somebody could implement in a functioning laboratory that's trying to push casework. Right now, it's terrific for somebody like me who's just doing research, and I can have a chemist sit there and do the manual manipulation of the data. But a lot of these folks don't have that luxury. They've got to have, for the vast majority of samples that they're trying to push through, some ability to automate that reporting, automate that data handling, automate the file archiving, all of this data handling stuff, so that they're not consuming as much of the technician time as they would currently. So, but I mean, it's obviously something that's understood there. It's just something we need to make sure that you understand what is needed on this end so that you can make the, I mean, it's a software fix. So.
One more observation for you. You would get a little, when you're right on the edge of some of those peaks that are really small, you would get a big boost in sensitivity if you could raise the peaks voltage. You may not have to go all the way up because you don't want to miss some things at the low end, but certainly running at 600 is too low to get the maximum sensitivity for something at 304. So that would help a bit.
So that'd help a bit.
Yeah. It might help enough in some cases to make it.
I don't know if it's going to help the probably, you know, as much as you need for some of those drugs, but yeah, it would help. I mean, there's stuff that still can be done. And that's, like I say, you're sitting right on the edge of probably what is enough sensitivity to really be truly useful in this. It's not that
whether
far
the
off.
gas separator will help for enough of those compounds or not, we don't know. It helps a lot for some,
yeah,
but we'll find out.
So I think there are, and this is where I say, is, you know, I don't want you to come away with a doom and gloom picture of this, that it just didn't work. It's so close you can taste it. And the stuff that's there, I mean, it's software. Software is fixable. We got some sensitivity things. Odds are those sensitivity things are fixable. And it really could be, a really beneficial instrument if those couple of things can get to where they need to be. And I think it's really possible to get them there. Minimal drug extraction, some of what we're talking about, like the micro extraction stuff. I mean, you got to do probably something currently to improve sensitivity. This was a bit of a shocker to us, but you know, you would think that if I did a really complete extraction that would have improved things dramatically, and it didn't necessarily. The clean bloods seem to work a little better than the nasty bloods. That's the case currently, even in a traditional analysis methods. Those nasty samples are just that, nasty. And it interferes with all kinds of stuff. Stuff grows, stuff develops, stuff decays. The samples are foul. Therapeutic drug levels, I mean, that's going to be more of a stretch because a lot of these drugs, therapeutic drug levels are probably maybe 3 to 4 orders of magnitude under where we're typically looking at. So great for overdose, and I think overdose is probably, you know, so for forensic tox, in large part, post-mortem forensic tox, you're looking at overdose. You're not looking at therapeutic. Now, that gets a little squishy in some places. I certainly have had cases where people have been interested in the therapeutic concentrations for some other reason that you never would have thought of. But there's where the benefit of a TOF could really give you an advantage, that you've got all those data there. If somebody comes back 6 months later and say, hey, did you happen to think if there was acetaminophen in there because we're thinking they may have taken Percocet? Let's go look. We can go back and see. I mean, that could be an enormous advantage to you. I've certainly had cases where that would have been vastly beneficial to be able to do that. I put in that caveat that we had a bunch of old stinky samples. Some of what we're seeing may be the result of old stinky samples. However, when we were doing more traditional analyses on these samples in modern day, not all cases did it look like it was just an old stinky sample that was creating the problem. Strong potential for the instrument. Implementation issues, I'm probably starting to sound like a broken record here now. Sensitivity, interferences, it's a mixture, which really probably just harks back to a sensitivity issue. And the software. Like I say, Chip's been a real good sport about me carping about the software. But Mass Center creates problems. Schrader looks to solve a lot of those problems. If the Schrader software moves on to where they're talking that you can actually acquire the data through Schrader and have Mass Center do nothing more than sit quietly in the corner out of your way, that would be great. But our experience with Mass Center is, as you saw yesterday, it's cumbersome for mass calibrations. The software itself is a little quirky and unstable. We've had odd things that make it crash. I think everybody who's been using it has odd things that make it crash. Data management in it is a little awkward and quirky, but again, these are software issues. This ain't rocket science, it's software. This is all solvable, and they're going a long way towards solving it. On the sensitivity, Chip, I think, is going to talk some about the GIST/vapor system that has some real potential for sensitivity. I have not played with it at all. I don't have one, so I really don't know specifically, but what I've seen certainly looks like it may have some advantages. There's that software thing again. Schrader software looks like it addresses a lot of these things, and I would encourage the manufacturer to continue proactive and aggressive pursuit of improving the software. We're still acquiring, in the current situation, you'd still be acquiring using Mass Center in the current version of Schrader. So you still have some of the Mass Center problems, but that may be going away. So, lastly, but certainly not leastly, Jerry Ropero-Miller is my partner at RTI. We get accused of, we only got checked out with one brain. Usually she has it, not me. She's on most of these grants. We flip-flop who's PI, who's co-PI on a lot of these projects, but I gotta say, most of the fun of working at RTI is because she's there. Nicole Bynum is the one who actually does all the work. NIJ for the grant funding. Can't do it without the money. Thank you. Leap Technologies, who's actually in Raleigh with us, they were very kind to supply us with the auto sampler. They brought it over. We had free use of it for quite a while. Maricopa County, Washington State Police, and OCME North Carolina were all happy, willing, and very kind to supply us with nasty, icky, sticky, ooey gooey samples that got them out of their freezer and put them in ours. And Spieware, they provided us all of the solid phase extraction materials, the manifold. That little manifold's about a $2,000 manifold, so it's relatively inexpensive, rugged little sucker. But Spieware has been real kind in providing that stuff.